want.
Okay. Okay, and thank you very much for the invitation. And okay, this is the title of my talk, and I will speak about some results obtained in collaboration with several people that I will say here. Before starting, let me just say just 2 words for Antonio. And I was a postdoc of Antonio, and I would like just so I learned a lot of things from Antonio. We worked for 2 years together. He taught to me to follow all the times the ideas. And okay, just to say thanks to Antonio for all what he taught to me. Okay, so the model that I'm discussing here, it's a model of stochastic particle systems that are a bit different from the usual one. So eta is a configuration. I will consider essentially a one-dimensional lattice all the times. And so the number of particles is unbounded, and you may have also some continuous variable in some cases. And so the difference with respect to the usual particle systems is that you may have that more particles jumps at the same time. So you have a rate, so you have a configuration of particles on a general configuration of particles, and then you may have a number q of particles that jumps at the same time, and the jumps is between nearest neighbor sites. So this is when the configuration is eta, and the rate of jump depends just on the value of the configuration of the 2 sides. And when the system is not in contact, so I will consider the cases when it's in contact with boundary reservoirs, but without this contact, the model is reversible with respect to a Gibbs measure that indeed will be always product. So the situation that I'm considering is when the system is in contact with some boundary reservoirs. So you can imagine that the lattice at certain point is embedded on an interval. And this contact with these 2 sources at the boundary is in the model enters in such a way that you have creation and annihilation of particles at the 2 extrema of the segment. And in general, so due to this interaction with the external source, the model becomes non-reversible. The invariant measure is not known. You lose the translation invariance. You have long-range correlation. So you have a lot of different situations that let the system difficult and interesting. Sometimes you have some combinatorial representation of the invariant measure, like the matrix and SATs for the exclusion. And sometimes you give some macroscopic description of the model in the scaling limit. And I recall a pair of results. So I think that among the first results on studying such stationary equilibrium states are the paper of Galvez, Kipnis Marchioro Presutti, and Kipnis Marchioro Presutti, where they start from the random configuration distributed according to the invariant measure. Essentially, they do the empirical measure and study what is called the hydrostatic behavior, and they show that it's converging to some profile that is linear in some cases. Just to quickly point out that, so this is the typical situation that you have these long-range correlations, in general, but there is a special case that is the zero-range model. I will just say a few words because I will consider generalized zero-range model. So for zero-range model, and that zero-range model, it's a model, this is a classical zero-range model where just one particle at each random time may jump, and the rate of jump depends just on the number of particles from the starting sites through a function that you call G. In that case, the invariant measure is always product. It's a product, but it's a product of inhomogeneous, so the marginal are not always the same. The measure is inhomogeneous, is a product of inhomogeneous, and in that case, in the one-dimensional cases, is linear, since this chemical potential solves a discrete Laplace problem. So this is the situation. You have the zero-range process. Particles enters with two different rates and the two extrema, and you have this special case where the invariant measure is its product. There are some models that are solvable. Let's say I'm saying that are solvable at the macroscopic level, in the sense that you can compute the large deviation rate function of the empirical measure that I wrote shortly here. So it's a convex combination of delta measures on points on the lattice that is embedded on the interval, and the weight of each delta measure is proportional to the number of particles that you have. So for the empirical measure, you can compute for some special model the large deviation rate function, and you may have either, for some model, you can use the representation of the invariant measure. For some other model, you can use a variational approach. The few models for which this is possible are essentially the exclusion process, the KMP process, and the dual one, the discrete KMP process. So for that few models, you have that if you go to compute the probability with respect to the invariant measure, that the empirical measure, this is a random discrete positive measure, is close to a given absolutely continuous density, is exponentially small with respect to a rate function. So the rate of exponential decay, it's this potential V of rho, and V of rho has a variational representations. A simple one sometimes is written as an infimum, sometimes as a supremum, sometimes you can write in the two different forms. And I will show you exactly how it is this form for a specific model that I will discuss later on. This is the Kipnis Marchioro Presutti model. On each lattice sides, you have a variable that is a positive real, assume positive real values. And it's interpreted as in the original model as the energy of an harmonic oscillator that is at the lattice sides x in lambda n. The dynamics in the bulk is as following. With rate 1, you take two nearest neighbor sides, you take the energy that you have there, and you sum and you share again through a uniform random variable. So the two oscillators enter in contact and share the energy, and the dynamics is conservative. So you put a fraction back on x and another fraction back on y, and the fraction is a uniform random variable in 0, 1. At the boundary, the interaction with the sources is like this. You have, let's say a Gauss site eta 0, and eta 1 is the first site of the lattice. At rate 1, the value of the energy at site 1 becomes this fraction here. So it's just the behavior is like in the bulk. And in the Gauss site, you put a new fresh exponential random variable with parameter t minus at the left boundary and t plus at the right ones. Since the exponential random variables at the two extrema are different, the model is not reversible, and the invariant measure is not known. But for that model, you can compute, as I told you, this is not a rigorous result, but you can apply this physical theory that is the macroscopic fluctuation theory, and you can compute the large deviation principle for the Kipnis Marchioro Presutti model in one dimension. So the probability to observe an atypical density is exponentially small with respect to this rate as V of rho, and in this case, V of rho is written as an infimum. So here there is this the density rho of x, and you have to minimize over the profile t that are monotone. At 0, take the values t minus, at 1, take the values t plus. this was proved in 2005 with Lorenzo Bertini and Joel Leibowitz. So you see here in this case, V of rho is the infimum over T of this joint functional on two variable rho and T. And the natural question here is, it is possible to interpret this as a contraction principle. So, and the answer is yes. This question was raised in a paper in 2007 with Lorenzo Bertini, Alberto De Sole, Claudio Landin, and Gianni Gavalasigno. And indeed, in that case, the functional that depends on rho and T, it's that one, and has a very clear interpretation, because this part here, it's a large deviation rate function for a product inhomogeneous measure of a product of inhomogeneous exponentials, where the mean depends on the position and is related to this function T of x, while instead this one is the large deviation rate function for the order statistics of uniform random variable, independent uniform random variable in the interval T minus T plus. So at the level of large deviation, there is this very nice formula of the large deviation rate function. And then the natural question is, do there exist also a similar simple form of the invariant measure also at the microscopic level that is true for each n? So this was essentially in a form of a conjecture in a paper, the paper that I said before in 2007. And so the conjecture is that the invariant measure of the Kipnis Marchioro Presutti model is such that you may have just a collection. So the eta are the random variables of the Kipnis Marchioro Presutti model. And the conjecture is due to the form of the large deviation rate function. Maybe it can happen that if you had just another collection of random variable, one for each lattice sites, the invariant measure assume a simple form. In particular, you want a distribution of the random variable eta and these ghost random variables tau, such that they have a joint large deviation function that is the one that you have here. And then this is easy to construct a model that has exactly that as a large deviation rate function. This is we call a toy model. You take these ghost random variables tau x that assume values on this interval. They are ordered, and they are distributed exactly as the order statistics of uniform random variables in that interval. Then the joint distribution with the random variable eta is so that once that you have the values of such random variables conditioned to the values of the random variables tau, the distribution of the random variable eta, it's a product, an inhomogeneous product of exponential, where the random variable eta of x associated to the lattice site x has a mean values that is T of x. So in formulas is this one. So the joint distribution of the random variable tau and eta, it's as this form here. Now you integrate over the tau, and you should get you get a measure that is a mixture of product of inhomogeneous exponential random variables, and this is a measure that has exactly the large deviation rate function of the IMPA model, including long-range correlations and all the characteristics that you have. So that was the conjecture. So this was the proposal. But then you go to try to check on the generator. It's quite difficult to insert a mixture and verify and try to verify if it is invariant measure. And you discover that it is not the invariant measure. Indeed, we were able at that time to verify just for n is equal to 1. That indeed the invariant measure is a mixture of exponentials, but the mixture was not the uniform one, but was this arc sine law. Okay. Okay. I will show at the end which is the solution for each n. But now I move to other model. And so for the KMP model, we were not able to solve this. And then it was it was natural to try to find other models, other microscopic models for which such conjecture that apparently was not true for the KMP model could be true. And according to this variational theory, the macroscopic fluctuation theory, so models for which the large variation rate function have a structure that is similar to this, so similar to this one, that can be interpreted as a large variation rate function, so as a contraction principle, so that V of rho can be obtained from a contraction principle. So from the general theory, comes out that you need to find some diffusive systems for which the diffusion coefficient is constant and the mobility is a second-order quadratic polynomial in the density. So to do this, it's also difficult because you need to find a model that is both reversible and gradient, because otherwise you cannot really compute that one, these transport coefficients. But then recently we met some models for which that was possible. So these are some generalized zero-range dynamics. So these are zero-range dynamics, like the one that I showed to you at the beginning, where the rate of jump of particles from a site X depends only on the number of particles that you have.
David?
Yes?
May I ask a question?
Yes.
So it's important that the polynomial to be convex, right?
Okay, I mean, so if the polynomial is convex, like in the KMP model, then the large variation rate function has an expression like an infimum, and then it's exactly in the form of a contraction principle. If the polynomial is of second order, like for example in the exclusion, then the classic expression for the large variation rate function is in terms of a supremum. So you cannot interpret directly as a contraction principle, but for any second order polynomial, you have an explicit form of the large variation rate function. What I think is possible is that you could also write this large variation rate function as an infimum. And I think that it could be the case that also in that case, you maybe find represented. So you could interpret also as a contraction principle, and you could find a representation like this.
Okay, thank you.
Indeed, for the exclusion, there is a recent paper by Floriani that do something similar. And indeed, for the exclusion process, you can write, since the spins are just 0 and 1, you can prove that any measure on 0, 1 to the power n can be represented as a mixture of product of inhomogeneous or inhomogeneous Bernoulli distribution. The important thing is to find a nice one. There is a recent paper by Floriani and other authors that that do a kind of representation like this. Okay, so these generalized zero-range dynamics are dynamics where on each site you may have an arbitrarily large number of particles, and the rate of jump of particles depends just on the number of particles that you have at the starting site. You have also some continuous models of this type, but differently from the one that I showed at the beginning. For this generalized zero-range dynamics, you may have that more than one particle may jump at the same time. So if you have 20 particles, you may have 10 particles that jumps simultaneously on another side. And this class of models we observed, so they were introduced in this series of papers. So I think that the original, so the one where they were introduced is the first one by Frasek, Jardinat, and Kurchan, and in the other papers they were studied and they were able to compute for the invariant mesh. So we were getting interested in this because they were able to compute exactly all the moments of the stationary non-equilibrium state. So, and the motivation for the introduction of this model was coming from integrable system in quantum models. So as I told you, for this generalized zero-range dynamics, the authors of the that I showed before, they are able to compute all the moments of the stationary non-equilibrium states. And then for us, they were good candidates to try to check this conjecture of 2007, because so this was, and then with Monia Capanna and Dimitris Tsakarogiannis, we investigated this class of models that were introduced coming from motivation from quantum models in terms of the transport coefficients. And we were able to classify exactly among the class of generalized zero-range dynamics, we were able to classify exactly which are the generalized zero-range models for which you have a constant diffusion coefficient and a second-order polynomial convex on the mobility. And the class, so it's exactly the one that was identified by Jardinat and the others. So that was so that was a good motivation. So this was a class of model for which we could try this to see if it is true that at microscopic level you have this nice structure of the invariant measure. And so because in general, so you have a large class of generalized zero-range dynamics, but the one for which you can really compute all the moments and for which you have this exactly this characteristic of the transport coefficient have a special form. Okay, so it's a large class. I will discuss just a special one. So the rate of jump, so when from site X, k particle make jumps, and k is any number between 1 and the number of particles that you have at X. The rate of jump has to be of this form here, with this factor 1 over k here, and this function g has to be of this form here. So I will not consider the general case, but I'm going to show, to concentrate on the simplest one, that is when this a is 1, and so the rate of jump is of this form here. So on a site X, if you have e of x particles, any number of particles k that is less than or equal than net of x may jump, and k particles jumps with rate 1 over k. This is called the harmonic model. Then you see that the total rate of jump from one side is given by this. That depends just on e of x. For that reason, this is a zero-range model. So the boundary-driven harmonic model, it's like this. Now you put in, so you put in contact with boundary reservoirs, and then you create and inlay particles at the boundaries with these rates here. So even at the boundary, you may create an arbitrary number of particles simultaneously. In particular, any natural, you can create k particles at the left side with a rate that is alpha k over k, and at the right side with a rate that is beta to the k over k. Alpha and beta are two parameters between 0 and 1, and so if they are different, the model is not reversible. And when alpha is equal to beta, the model is reversible, and the model is the invariant measure is a product of geometric random variable with a given parameter that depends on the boundary on the boundary sources. So m is the mean value of the geometric. Then when alpha is different from beta, the stationary, so the model is not reversible, and the station, so you have a non-trivial invariant measure. And then for this model, we can really prove that the conjecture is true exactly in the form that we were trying to find for the KMP. So the invariant measure for the boundary-driven harmonic model is written in this form. So it is a mixture of product of inhomogeneous geometric. These are the parameters that are related to the boundary. And the distribution of the parameter is exactly the order statistics of n uniforms on this interval that is related to the values of the sources. And this has been showing this paper here. The proof the approach is a computational. So at step one, we write just the stationary condition in terms of the moment generating function. The step two is we show that the result is true for one single oscillator. You don't need to know. So if you do the suitable change of variable, you then not to do a lot of computations, but you have to do it in a correct way. So it's true for one. And then the step three is that the case n can be reduced to the case where you have just one single oscillator. And this is because the distribution of points is such that, so these are the parameters of the order statistics. If you fix all the points, then all the points apart one, then the distribution of this, it's on the interval that where it can move, and has the same law as just one single point. And then you can reduce the case of n to n different one-dimensional computations, and you can really solve. So this is a direct computation, but you have to proceed in a careful way. We are working, we are working just now on the generalization to, as I told you, this class that was introduced by Giardina and the others, it's large as a more general class of models, and we can do this also for the other class of model. We are working just now on this. In that case, you have not the distribution of the parameter is not the order statistics of uniform, but is a generalization. So the order statistics of uniform, it's so if you have an order statistic of uniform, you can imagine also that the length of the interval that you create are exponential independent random variables conditioned to have a total sum that is fixed. So for the general case, you have that you have a similar distribution, but instead of exponential for which you get the order statistics of uniform, you have to put gamma distributions. So it's more complicated. And the same results has been obtained also in this paper by Carinci, Franceschini, Frasek, Giardina, and Redig. So they proved this representation of the invariant measure for the whole class of models using the explicit form of the moments that were computed in the previous in the paper where the models were introduced. Well, he said we can do this without using in a complete independent way, without using the form of the moment. Okay, so up to now I just show it to you the form of the invariant measure, and it is a static computation. So I have a model, I have the problem to compute the invariant measure, and I try to introduce new variables directly on the invariant measure, some Gauss variables, and I try to find with these Gauss variables a simple representation of the invariant measure. So this is a static approach. This works just on the invariant measure. But then a natural question is, can you? So this is it's something that holds just for the invariant measure, or maybe you can do this in a dynamic way. So you can do a coupling. So these Gauss variables, you can construct the process, the boundary-driven process that you are considering, and doing a coupling with these Gauss variables and consider a dynamics, such a way that so the invariant measure for the variable eta and the Gauss variables is simply the invariant measure of this enlarged process. Well, this is a natural question. And so we can answer to this question, yes, for the KMP model. And this is a paper in collaboration with Anna De Masi, Pablo Ferrari, and myself that we just finished. And so for KMP, so for zero range, there is this magic that the computation for one single site, and this is due to the fact that it's zero range, allows to get the computation for all the n. But for KMP, it doesn't work directly. And then, so we do this alternative approach. We do this dynamic construction with a coupling of the dynamics. So the variables of the KMP process are the energy associated to the different oscillators of the dynamics. And we introduce such Gauss variables that are tau of x that you can interpret as the temperature of the oscillators at the site x. And so the couplet dynamics, so you can look at the couplet dynamics from several perspectives. I will show to you the one that is more physical, but it's the one for which you really do not understand why it works. And the couplet dynamics in that case is like this. So as you say, at rate 1, for the KMP process, you have that at a pair of nearest neighbor sites, you have these pairs of energy. And at rate 1, this is the evolution of the KMP. You share again the energy with using this uniform. This dynamics is conservative. So what does it mean? This, that the two oscillators that you had at x and x plus 1, they enter in contact and they share some energy. They exchange the energy. Then physically, what happens if the two oscillators enter in contact? They share the energy. They are in contact, so they go to the same temperature, and they thermalize. So indeed, the couplet dynamics is like this. So either do just the KMP process boundary driven. Here I'm showing to you just what happens in the bulk, but a similar construction you can do also at the boundary. So when there is this exchange of energy, at the same time, the two temperature of the two oscillators that you had before you do this resharing of the energy, they change. They go to the same temperature because they went in contact, so they thermalize, and they go to a common value that is this one. So it's a convex combination of the previous values of the temperature. So you have this joint evolution of the energy and the temperature of the oscillators. When the oscillators exchange energies, the temperature, they go to the same value. That is just a deterministic function of the energies and temperature before the jump. So this is a joint evolution. And at the boundary, this is similar. It's a joint Markovian evolution where eta do KMP and the tau do an evolution that is a complete function of the evolution of the KMP and the temperature itself. As I told you, this is physically it's natural, but it's difficult to see why it works. But okay, I decided to present that way in this time that day. Then for this couplet dynamics, so you have this pair of random variables that evolve like this, the eta and the tau. For this pair of random variables that do a Markov process, you can compute the invariant measure. And again, you can compute introducing other random variables, but an invariant measure is like this. So the random variable tau are distributed according to a measure, that it's the invariant measure of an auxiliary opinion process that I will explain later on. And once that you have, so conditioned to the values of the variable tau, the random variable eta are independent, are distributed as they are independent, but are distributed as independent inhomogeneous exponential random variables of mean value tau of x. So You before distribute the tau, and then conditioned to the tau, the eta are independent and distributed according to inhomogeneous exponential random variables. Just a curiosity, so here, the random variable, so in the evolution, in the pair of random variable eta and tau, you have that the evolution of the tau is following the evolution of the eta, so it's completely a function of the evolution of the eta, while instead the invariant measure, so the natural way of looking at the invariant measure is the opposite. It is natural before to generate the random variable tau, and once that you have the random variable tau, you generate the eta according to this product of inhomogeneous exponential. So the proof that I will not show use a coupling with an equilibrium KMP process where it is transparent why the invariant measure is of that type. And then another coupling allowed to extend this also to the discrete KMP. So a coupling between the continuous and the discrete KMP process allows to extend this also to the discrete KMP process. And now I'll show to you the opinion, so the auxiliary opinion model that is associated to this part of the invariant measure. And so this is the opinion model. I continue, I call the variables again tau, but you have, so you may think that so these tau's are really related to the variable tau that I introduced before, but be careful that the random variable tau here in this joint evolution that I'm describing here are not doing in general the opinion process, because if you look just at the random variable tau, they are not Markovian. Okay, in some situations, so in the stationary case, for example, the tau, they do a Markov process that is exactly this opinion model. So this opinion model is related to the evolution of the tau that are coupled with the KMP process, but it is not that this is the evolution of the tau, because in general it's not Markovian. So you may think this is as an auxiliary process that is related, but is a Markovian process just on the tau. So the random variable tau, they are ordered, are in the interval tau minus tau plus, and then the possible configuration are so that at each time I may have that some of the values of this tau are coinciding, they are assuming the same value, but I may have that, so if I have two different variable tau that assume the two different values, only two is possible. I cannot have three or more random variables that assume the same value. So just with a picture, the possible configurations that are in my opinion model are the following. This is a good configuration because all the tau are different. So these are tau is so where there is the blue cross, this is the value of the tau. This is another possible situation. So you see here there is a value where there are two values of the random variable tau that are coinciding, and the other are different. This is possible, or pairs of tau. This is okay, and this is not a possible configurations of my opinion models. And if you think, so indeed, if you think a chain of oscillator that when they enter into contact, they take the same temperature, and if you start with the temperature that are all different, if you think a bit, you will immediately realize that if you look at the temperature of the oscillator, you will have only temperatures that are equal only in pairs. You may not have three or more. So, and the rate of evolution of the opinion process is the following. At rate 1, take a pair of tau that are near stable. At rate 1, they go to the same value that is uniformly distributed in the interval between the two. And okay, this is okay. And this is an opinion model, so you may imagine that these are two individuals. The value of tau, it's an opinion, and when they they enter in contact, they speak, and they go to the same opinion that is uniformly distributed in the segment that is dividing them. At the boundary, you have this evolution. The last one goes to a convex combination with the top plus. You imagine that at the top plus there is an individual that is an extremist, and at minus another one that do not change the opinion, but the two individuals that are near, they are changing, like in the general case. And this is the evolution of the opinion model. We show some examples of the evolution. You may observe that for n is equal to 1, you have just one individual that is moving here, and at rate 1 goes uniformly to the right, at rate 1 goes uniformly to the left. This is a simple Markov chain on the interval, and then invariant measure you can compute, and it's the arc-sine law, the one that we got in 2007. But instead, if you have more than one oscillators, in general, the invariant measure is not known. And we have several dualities for this model. We can compute the correlation for the stationary non-equilibrium states, and we can do the hydrodynamic, the hydrostatic, that is the convergence to the linear profile using these correlations. And okay, and these are the examples of the evolution. So here you have a possible configuration. On the left, you have a possible configuration of the opinions of the individuals, and here you have all the possible evolution. So here, this is a configuration. These two individuals here, they enter in contact, so they share this, they agree on the same opinion that is uniformly distributed here, and the new configuration is this. So you have no more two individuals on the same side here, but you will have two here, and the other one are there. This individual is entering contact with the extremist to the left and goes here, and the new configuration is this. Here, these two individuals enter in contact, and you create a new pair of individuals that have the same opinion. Or the last possibility is that this is entering contact with the extremist to the right and is moving here. So the number so this is the new configuration of the model. So this is the model, the opinion model that it's so the invariant measure of the KMP process. It's just too much behind. So the invariant measure of the KMP process is obtained integrating the variable tau and looking just on the eta. The eta are the variable of the KMP process. And here you have to put exactly the invariant measure of this auxiliary opinion process. And okay, and Chiara told me that the talk was 45 minutes, and I think that I was perfectly in time, and I think that all is what I wanted to say, essentially.
Okay, thank you so much, Davide. If you want, you can unmute your microphone. We can thank Davide properly. Now let's see if there are any questions or comments. So in fact, I have a question from exactly from the slide that you were before, 25. I was wondering if this auxiliary opinion model is the same for the discrete KMP, or is a different one?
For the disk, it is exactly the same. Yes, it is exactly the same, but the random variables are geometric. Yes, are geometric.
Yeah, so the product is not the exponential, but it's geometric, but the auxiliary model is the same. I see.
Yeah, I think yes, it's
okay. So I have a question, actually a couple of questions, if I may.
Yeah.
So the first one is that So in the KMP, so the dynamics is like so you add the energies and then you distribute it uniformly, right? So if in this dynamics you do the following modification.
So in the KMP, no, it's not uniform. I don't understand sorry.
Okay, just the KMP dynamics, no? So when
yes.
when the clock rings, you do this uniform.
Yeah.
But then if instead of uniform, you take any distribution which is centered at 1/2, you also get a model with linear diffusion coefficient and convex quadratic, the other guy. How do you call it? Mobility? I don't remember.
Mobility. I don't think so. You need some constraint.
Yeah, well, maybe my computation is wrong. I was doing this computation.
No, I'm saying that I'm not sure. Maybe you are right, but I think you need something on the second moment too, not only the first one.
Yeah, no, yes, of course, but I think you just need the second moment to be okay. So I think it's if it's symmetric around 1/2, it works.
I'm not sure, but maybe yes, but I'm not sure.
Okay.
Yes. There are a lot of models for which yes, you can do models like the KMP for which this works. Yes.
Okay. But then should this also work, this type of thing that you are explaining to us?
Macroscopically, yes. So so at least this macroscopic fluctuation theory tells you that at least it's not a theorem, but it's so if you have a diffusive system that has a diffusion coefficient that is constant and the mobility is quadratic, then the structure of the large deviation rate function it's very similar to the one of the KMP. So you have to modify a bit but the structure is exactly that one.
Okay.
It depends how so maybe in equilibrium we'll not have a product of exponential as invariant measure. We'll have other random variables, and then there will be the part of the inhomogeneous. So let's say that
okay,
you will have a part. My computer is slow, but here. So here, the large vector function. So if you have a constant diffusion and a quadratic mobility convex, a second order polynomial that is convex, the large deviation rate function will be of this type here. What is changing is that part here, because you do not have necessarily an exponential, but you will have a part that is a kind of Kramer functional for the kind of marginal that you have for your model. And then at the macroscopic level, it's as this structure, but this doesn't mean that at the microscopic level, so for each n, you have a structure like this. But and indeed, so to have a result of this type, you have really to build up the model microscopically in the correct way, because if you change that just a bit the model macroscopically, you lose this really, that instead the macroscopically it's more robust, so you have all the time. So, but the answer is that okay, this is a good model for proof this. So where the invariant measure could be of this form.
Okay. So the other question. So actually, Pablo was presenting similar. Well, it was presenting the same result, but of course with a different perspective in the colloquium last month here.
Yeah.
And so he was explaining a little bit about the proof. So there were something there about exponentials and uniforms that do some magic.
Yeah.
And I went home and discovered that so if you replace exponentials by gammas and uniforms by betas, you get the same magic.
Yeah, something. Yeah, I can imagine. Yes, indeed.
Yeah, that wouldn't allow you to do the to find a microscopic model also for the case of the gammas.
Yeah, as I told you, so for these zero range models, okay,
Yeah.
then you have this with this gamma distribution. So so there is this whole class that has a lot of gamma distribution there, and then there is this magic. So it is true. It's an identity. It's true, and it also a representation of this type, where instead of order statistics, you have that the intervals in which is split the interval between t minus t plus. It's so our IID gamma distribution conditioned to have this sum that is fixed. And yes, I think that is very interesting to find models, continuous model like KMP, to search for models that have this macroscopic integrability, and to try to do a similar computation. I think that could be possible, yes. But
Okay.
so yes.
Okay, I think that's it from our side.
I have a question.
Yes.
Davide, I wanted also this page 10. You are now. I am curious about this second term. The row doesn't appear there. Why is it? Can you comment on that?
Can you? I can listen not very well. What can you repeat?
Yeah, the row does not appear in the second term of this formula.
This one that it's here.
Yeah.
Yes, this is exactly because the form of the distribution of at the macroscopic level. So the form of the invariant measure, it's so the variable. So let's say let's go here on the toy model for the zero range dynamics. So here, you see. So why then, if you look at the distribution of the M, so if you look just the marginal of the M, so this is already integrated. Forget about this integral. No? But if you look at the joint distribution of the M and of the eta, if you integrate out the variable eta, you get that the distribution of the M is just the order statistics. Okay, so it's a so the variable M, the ghost variable, have alone a very simple distribution, while instead the variable eta alone have not a very simple distribution. Okay, so if I do the marginal on the eta of this measure, it's a complicated measure with long-range correlations and so on. If I look just the marginal of the ghost variables, they have a very simple distribution. It's the order statistics of uniform, and that's you recover here on this formula for the large deviations. Sorry. So this is similar. So if you go to do contraction, so you have to minimize over the row. You can minimize over the row just taking rho is equal to t here. This term here is 0. And you recover just this term here, that is just the order statistics of the large deviation for the order statistics of uniform. Okay, so the reason why these terms don't contain rho is that, okay, it's the same on the measure. The marginal on the ghost variables alone, it's simple, and it's the order statistics. This is
okay, thank you.
Okay, let's see if there are other questions or comments. Okay, if that's not the case, let's thank Davide again. Thank you, Davide. And we update next Wednesday. Thank you, everyone. Bye-bye.
Bye. Thank you. Ciao, Davide.
Ciao.
Grazie. Buona serata.
Grazie Davide, buona serata.